Okay, we are back. Hopefully you have time to try this question yourself. Alright, otherwise please pause the video and do so. Right, we'll move on to solve the question together if you have already tried it. Okay, there are three charges, one at B, one at C, one at D. B and C are positive, D is negative. Alright, what's the electric potential and electric field strength at corner A due to the 3-point charges in terms of R and Q? Right, we need to first think about whether this one, electric potential, is scalar or vector. We should realize this is a scalar, alright? And this is a vector, right? So they must be treated differently. If I want to find the electric potential at A, I can call this V of A, right? This is equal to the potential due to B at A, which is equal to 1 over 4 pi epsilon naught plus Q, right? Remember, for potential and potential energy in electric fields, we substitute the sign inside because they are scalars, right? Vectors don't need because the sign is representing direction and should be shown in the diagram. Okay, divided by this is R, so I call this R. Right, that's for B, right? So this is the potential for B. Then for C, we look at it again, 4 pi epsilon naught minus Q, right? Be careful, oh sorry, plus Q also, because this is still plus and this is plus, right? Then divided by the distance of C from here, right? Just now this one easy lah, is R, because given the question, what is this? You can Pythagoras theorem to get square root 2R, right? So this is square root 2R. Then finally we plus 1 over 4 pi epsilon naught minus Q, because this is minus Q over R. Okay, so you sum all these things, you press all values and leave Q and R alone. So this is plus, this is plus, this is minus. Okay, so this is plus this thing, but this thing is negative. So you must pay attention to the minus here. Right, so this positive, positive, negative. Right, so if you do the calculation, you get something like that. And you take out all the numerical values, leave Q and R alone, you get this. Okay? For electric field, you have to do it as a vector because field is a vector. So electric field of B at A, right? Electric field of B at A is equal to 1 over 4 pi epsilon naught Q. Actually, this one I don't need to sub the positive or negative already because I already show the direction in the arrow here. Can you see this arrow here? Already shown direction, right? Because positive charge, the arrow is outwards. Right, so I don't need to plus anymore because plus already represented in the direction of the electric field direction. Right, so divided by R squared because that's the formula. Then E of D, which is due to this one, electric field at A due to this charge minus Q, will be same magnitude by this direction because negative charge is inwards. So E of D is 1 over 4 pi epsilon naught Q. Again, I don't care about the charge sign anymore. Vectors no need. So force and field no need to care about the sign. Energy and potential energy, potential and potential energy need to care about the sign, right? So this is over R squared. So you realize same magnitude, ED and EB have the same magnitude because same Q and same R, right? But EC, because it's in this direction, you see the direction, the distance between the charge plus Q and point A, right, is larger. So EC should be 1 over 4 pi epsilon naught again Q divided by square root 2R squared. Right, so EC should be a smaller vector because the numerator here is larger than R squared. Right, so since this is bigger, EC is smaller, right, as a vector. So now I need to vector sum these three things, ED, EB, and EC, right? So vectorially is given the calculation here. I'm not going to do it for you because you should be very familiar with this kind of calculations now, right? You try to do it yourself, right? Pause and have a look at the answer. You have to also have to calculate the angle. Okay, can? I assume you are able to handle this, right? Then we'll move forward. Right, electric potential energy of 2-point charges, right? The formula is given by UE equal 1 over 4 pi epsilon naught QQ over R squared, right? Contrast with gravitation, is U equal to minus G MM over R, right? No square. I hope I didn't say square. This one got no square, right? Only the field and the force got square. Right. So anyway, back to what I was saying. Yeah. this is the gravitational equivalent of gravitational potential energy. Like I said before, gravitational potential energy negative must always keep one, right? Gravitational potential also always negative. This is because of the derivation. Okay, then but what about potential energy, electric potential energy, right? This one, it really depends on Q1 and Q2 are what type of charges. Okay, so I assume you understand this type of thing. I don't think it's difficult for him, right? So if I just tell you the simple summary you can read this part as well, right? But I'll give you a summarized version of what this part is saying. Let's say if I look at this formula and Q, big Q and small q are both positive, right? Then remember for U and V for electric potential energy and electric potential, I will substitute the sign in the charge. That means I'll substitute positive some value for Q, let's say it's plus 8, then small q maybe is plus 1. So plus 8 times plus 1 guarantees that my U here is positive, right? If, let's say it's minus 8 multiplied by minus 1, means what? Both these two charges are negative. Then can you see that I still get positive U? Right? So anytime you multiply these two charge to get positive, or you multiply two negative charge to get positive, U is always positive. Understand? Right? So if these two are positive, positive, or negative, negative, in both cases, the potential energy of these two charges are positive. Okay? So when is it negative then? Right? So it's negative when, it's negative when the charges are opposite sign. Okay? Right? So if, let's say Q1, Q is negative 8 and small q is plus 1. Then minus 8 multiplied by minus 1 will make U negative. Likewise, the other way around, plus 8 minus 1. Also, U will be negative. So anytime your charges are opposite sign, potential energy is negative. Okay, you can just memorize that just for calculation purposes. That's all you need to know. Okay, so that's what is being said here. Right, so they say in a bit long-winded way, but it's fine also. If you understand this is okay, but basically what I summarized earlier. Okay, and potential energy is the shared property of two charges Q and Q. So it's a consequence of interaction between two bodies, right? If the distance between two charges is changed, the change in U is the same whether or not Q is held fixed or Q is moved, right? That means big Q is stationary, small q move, or the other way around. Small q is fixed and big Q move. So we never use the phrase electric potential energy of a point charge, right? It's always electric potential energy of a pair of charges. All right. Same with gravitation. You cannot say gravitation, no potential energy of this mass. Right? It's gravitational potential energy of this mass together with the Earth, for example. Okay. All right. So let's do a quick example here. Okay. Double ionized negative charge O2 minus travel from A to B, then to C. All right. You try this yourself. We'll come back in a moment to discuss. Right, we're back from the pause. I hope we have found time to discuss. Calculate the change in electric potential energy of this ion as it travels from point A to B. Right, so I go from here to here. And its final KE when its initial KE is this given amount. All right. So first, let's think about what we know about potential and potential energy. All right. If you remember from gravitation, the relationship between gravitational potential energy and gravitational potential is this. Then for electric field, it's the same thing, right? Just that this become Q, and this become V, right? More or less the same thing, right? The difference is that, again, because here we are dealing with the scalars, the Q here, please substitute with sign, right? Last time mass don't care, mass only got one type of mass, so you don't have to care about the sign. But the difference is when you deal with electric field or electric potential energy and electric potential, this Q here, please sub with sign. That means if negative charge sub negative charge like in this case, right? So change in potential energy of this ion has traveled from A to B, right? So change in potential energy is Q. In this case is negative 2, right? Right. So it's actually equal to negative 2 times 1.6 times 10 to the power minus 19, right? Delta V is final minus initial, so minus 5 minus 10. And so final minus initial. and you can press your calculator to get the change in U, right? So the change in potential energy must cause it to gain or lose Ke, right? We look at this, this is negative, so this one will be some positive value. I haven't pressed the calculator yet, later I'll show you the answer, right? But I'm just trying to think about the consequence of this motion, right? So my delta U in this case is positive, which means I gain electric potential energy. If I gain electric potential energy, I should lose Ke, right? So if I use my conservation energy, initial equal final, right? Or I can just use gain equal loss, right? So let's say delta U, which is the gain in potential energy, equal to the loss in Ke. So loss in Ke is Ke initial minus Ke final, and this equals to the delta U I calculated here, right? Then I try to find Ke final. Okay, what's the change in electric potential energy of this ion from B to C? Right, change in electric potential energy of this ion from B to C is 0 because in this case delta V is 0, right? I go from minus 5 volt to minus 5 volt. This is an equipotential line. So delta U equal Q times delta V, but delta V is 0, so this thing must be 0 as well. What's the change in potential energy of this ion from point A to C, right? And this motion over here, right? You can think of it as a vector sum of this motion and this motion, which means that the change in electric potential energy is just due to this, which means the answer is this one. Okay? Or you can just apply this formula again when you go from here to here. You realize that the formula applied exactly the same way. It's still minus 2 times elementary charge multiplied by delta V, which is still minus 5 minus 10. Okay? All right, I'll show you the solution. Right? So delta U I should get as some positive value here, which is this positive value. By conservation of energy, gain in U, which is what we calculated here, must be lost in Ke. So the final Ke is actually initial Ke minus the gain, right? Okay, so this one will produce this one. So Ke final equals to Ke initial minus delta U, which is the gain. All right, then part 2 is 0. Part 3, as I said, is the same answer as this part. Okay, we'll move on to, we'll keep this for the next lecture, right? We're hitting 12 minutes.